Okay, in this lecture problem I show you all of these different reactions and I ask you to determine if they're going to be SN1, SN2, E1, and E2. Now in order to understand or answer these questions, we have to remember some things that I've talked about in an earlier presentation in greater detail. I'll put a link to that presentation right here in case you want to go back and review it. The sum up of that presentation is as follows. In order to determine if a substitution or elimination reaction is going to go either SN1, SN2, E1, or E2, I'd usually just ask myself the following three questions in this order. Number one, is the carbon that's bonded to my leaving group primary, secondary, or tertiary? If it's primary, then your reaction is going to be SN2 or E2, potentially. If it's tertiary, then it's going to be SN1, E1, or E2. And if it's secondary, or if it's a stabilized carbocation, such as a benzyl or allyl carbocation, then it could potentially be any of the above. So I go ahead and write those things down, and then I go to question number two. Question number two says, is my nucleophile or base strong or weak? Now, if it's a strong nucleophile or base, then your reaction is going to be a 2 reaction, either an SN2 or an E2. If it's a weak nucleophile / base, then your reaction is going to be a 1 reaction. Question number 3, is my nucleophile / base a nucleophile or a base? Now this question, if I determine that the nucleophile / base is a nuke, that is a nucleophile, then your reaction is going to be a substitution. If it's a base, then your reaction is going to be an elimination. Now parenthetically, I need to mention this. For my classes, any nucleophile / base that looks larger than ethanol, whose structure is drawn right here, in case you forgot what ethanol looks like, when you draw it on paper, is a base and will do an E reaction. Anything smaller is a nucleophile and will do an S reaction. Now there are some exceptions. Although acetate, whose structure is drawn here, might look larger than ethanol on paper, it is a nucleophile and will do an S reaction. Also, negatively charged carbon and sulfur atoms are usually nucleophiles regardless of their size. Now, I realize I've thrown all this stuff at you very, very quickly, and you might not have your brains wrapped around it in a complete sense, but if you want a more in-depth review of this, I'll post a link to a lecture in which I do that. Now, one thing I want to state, just to remove myself from liability in case there are any purists out there who are looking at explanation number 3 and realizing that it's not 100% true all the time, please understand that I acknowledge that. These 3 questions that I go through are generally true and will take you to the major product of 90% of the questions you get out there and maybe more. And that is all I'm interested in. I don't like wading through the minutia of exceptions or details or other things like that, because I'm trying to teach students to just wrap their brains around this concept in a simple manner. Once you understand all of the basics and then encounter an exception later on, it's much more easy to deal with it rather than have me inundate everyone with all of these exceptions so that there seems to be absolutely no rhyme or reason to the subject. Okay, hopefully that sounds like a good enough cop-out on that. Let's go to our question. This first reactant here, when subjected to KOH, is actually under SN2 conditions and will give this as its major product. Now before I go on, I want to make sure that it's clear. I'm not trying to claim that when you take this molecule and treat it with KOH, you're never going to get an elimination or E2 product. That is not true. I'm trying to state that the major product that you will get, at least by my rules, is going to be the SN2 product shown here. This molecule over here, when treated under these conditions, will undergo an SN1 reaction to give the product shown here. The molecule down here, treated with sodium hydroxide, will undergo an SN2 reaction to give this as its major product. Molecule over here, where OTS is a tosylate group, all that is a good leaving group. Treated with water and heat is going to undergo an SN1 reaction to yield this product here. The molecule down here, treated with tert-butanol, shown here, is being subjected to E1 conditions and will yield as its major product this molecule shown here. And this alkyl iodide, when treated with lithium tert-butoxide, is being subjected to E2 conditions, which will yield this as its major product. Now, if you guys have any questions regarding these answers or want to know why they are the way they are, I will show those to you right now.
This is a fun set of problems, determining if a reaction is going to be SN1, SN2, E1, or E2, and then identifying the major product. Now keep in mind, and I've said this probably too many times in my videos, the rules that I use to be able to figure the answers out of this type of question are not always 100% true in all cases. And what I'm saying is, if you have an organic chemistry teacher who shares with you a reaction and writes down that the product of that reaction, SN1, SN2, E1, or E2, is different from what you'd predict using my rules, please don't lose your faith in organic chemistry. What I'm trying to say is that my rules, as far as I know, generally will lead you to what is the correct answer, or the major product, about 95% of the time. And beyond that, my rules are very, very simple and easy to understand, and that's the reason why I like them. I like to teach general rules that are applicable in the vast majority of cases, and then deal with exceptions as they come. With that said, let's look at each one of these examples and see if we can figure out which of the reactions it is. Remember, by doing so, we go through 3 questions. You'll see me go through these questions again and again as I undertake these examples. So this first one, we look at this starting material. The question that we ask ourselves first is the carbon that's bonded to the leaving group primary, secondary, or tertiary, or stabilized? Here is the leaving group, it's a bromine, and here is the carbon that is bonded to it. Now that carbon is a secondary carbon, but it's a secondary stabilized carbon because it's at the benzyl position. So because that is a secondary carbon that is stabilized, this reaction thus far could potentially be any of the above. So I go ahead and write down SN1, SN2, E1, or E2. I don't know. I have to go on to my next question. My next question, is my nucleophile / base, the KOH here, strong or weak? As you can see by that, looking at that KOH, that is a strong nucleophile / base. But the strong guys are going to do 2 reactions, either SN2 or E2. So I can cross off SN1 or E1. The last question that I ask myself, is the nucleophile / base a nuke, or is it a base? If it's smaller than ethanol, then it's a nuke. If it's ethanol or larger, then it's a base. Exceptions are acetate. Acetate looks like this. It's going to be a nuke. And another example are sulfides of any size. This sulfur could be attached to something big, and generally speaking, sulfur nucleophiles, this could have a minus charge or not, will be nukes. So these guys are going to be nukes. So as you can see, OH minus is smaller than ethanol, which means that it's a nuke, which means that it's going to prefer to do substitution. Remember, the letter N in SN1 or SN2 stands for nucleophilic. So I'm going to cross out E2. It is going to be an SN2 reaction. What that means, of course, is that OH minus is going to come in here, attack that carbon, and kick off the bromine. That will give me this product, plus my bromide leaving group going into solution. There will be an inversion of stereochemistry at that position. Now, because I've drawn this line straight, that indicates that this is a racemic mixture of both enantiomers at that stereocenter. If, however, I had drawn either a wedged bond or a dashed bond, then I would have the opposite configuration in the product. Remember that in an SN2 reaction, the nucleophile has to come in from the opposite side, or the back side, or from which the leaving group is attached. Hence, you get an inversion of stereochemistry. All right, we'll go through our questions a little bit faster for this example. Once again, this is the carbon bound to my leaving group, the bromine. Is it primary, secondary, or tertiary, or stabilized? If it's primary, it's going to be either SN2 or E2. If it's secondary or stabilized, it could be any of the above. If it's tertiary, then it can only be SN1, E1, or E2. So right here, we look at that thing. That is not only secondary, but it's also stabilized, which means that it could be any of the above. So I'll go ahead and write all of them down right here. SN1, E1, SN2, E2. Now I go to my next question. Is my nucleophile / base strong or weak? It's an oxygen that only has lone pairs to react with. It does not have a localized negative charge on the oxygen. It's not bound to a lithium or potassium or sodium or any other left side metal on the periodic table. Hence, it is weak. What do weak guys do? Weak guys do 1 reactions. And you can remember that by remembering that the word weak starts with a wa sound, weak, and so does 1, weak, 1, wa. So I'm going to go ahead and cross off the 2's. I've got either SN1 or E1. Then I go to my next question. Is my nucleophile / base a nucleophile or a base? Remember, we do that based on size. Nucleophiles are smaller. They can get in there. Bases are larger and bulkier, and they have to just steal hydrogen. This guy is smaller than ethanol when I draw it on paper, which means he's a nuke. So this reaction is going to be SN1. What does that mean? Well, what it means is that this leaving group is going to take off, giving me a stabilized carbocation. This is the slower rate-determining step of an SN1 reaction. Then my nucleophile / base, my methanol in this case, is going to come in here with its lone pairs. And then presumably another molecule of the solvent, the methanol in this case, is going to come and deprotonate that, pumping the electrons in there to give me my final product. In the previous example, where I had an SN2 reaction, I told you that there would be a complete inversion of stereochemistry. In other words, if I had actually drawn a wedge or a dash to that bromine, I would have the opposite wedge or a dash to that oxygen. In an SN1 reaction, however, that does not occur. Because I've got this carbocation, I don't have the leaving group appended solidly to it, either wedge or dash. This methanol can come in from either side, in theory, with equal ease. Hence, I'm going to have a racemic product here, as indicated by the plus minus sign. Now looking at this example, is my carbon bonded to my leaving group, in this case a chlorine, so I'm talking about that carbon right there, primary, secondary, or tertiary? Well, it's secondary, which means that it could be any of the above. So I'll go ahead and write them all down. SN1, E1, SN2, and E2. Now I go to my next question. Is my nucleophile / base strong or weak? Well, at sodium, it's a group 1 element bonded to an oxygen. It essentially pushes all its electrons away, so I can think of this as being an OH minus. That is a localized negative charge on an oxygen. That is strong. Remember, strong does 2 reactions, so I can cross off my 1 reactions, my SN1 and E1. Now I go to my next question. Is my nucleophile / base larger or smaller than ethanol? Remember, if it's ethanol or larger when I draw it on paper at least, then it's a base, with the exceptions that I showed you earlier. If it's smaller, then it's a nucleophile. It means it's small enough to actually get in there and kick off a leaving group. OH minus is indeed smaller than ethanol, so it's a nuke. Because it's small, it's a nuke. That means it's going to do a substitution reaction, which means it's going to be SN2. I can cross off E2. So what does that end up meaning? It means that this OH minus comes in here as a nucleophile, forms a bond with that carbon, pushes the chlorine off, and then bonds at that position. What is the stereochemistry pointing to that OH? Well, because this is an SN2 reaction, the OH has to come in from the back side, kicking off the chlorine in one step. Wha-bam! The chlorine was pointing three-dimensionally towards us. Because the OH has to come from behind, it's going to be a dash. It was a wedge to the chlorine, and of course chloride is going to walk away as a leaving group, SN2. Looking at this example, here is the carbon right here that is bonded to my leaving group, OTS. Remember, OTS is a tosylate group. It's a really good leaving group. You don't have to freak out and wonder too deeply beyond that what it is. You can look it up if you want. Is my carbon bound to my leaving group primary, secondary, or tertiary? Tertiary. Well, of course, it's secondary, so that means it could potentially be any of the above. So I'll go ahead and write down all of them, SN1, E1, SN2, and E2. Next question, is my nucleophile / base strong or weak? There are no localized charges anywhere on that molecule. There are only lone pair electrons on the oxygens. So this is weak. Now, we should be glad, by the way, that water is a weak nucleophile / base, or else it would burn holes in us when we drank it. So I'm glad. Because it's weak, that means that it could be a 1 reaction. Remember, weak starts with a wah-wah-wah sound, and 1 starts with a wah-wah-wah-wah-wah sound. I said too many was there. Anyway, so we're going to go ahead and cross off our 2 reactions, SN2 and E2, and we'll stick to the SN1 or E1. Next thing, is my nucleophile / base a nuke or base? That all comes down to size. Remember, if it's smaller than ethanol, it's a nuke. If it's larger than ethanol, then it's a base. And if it's the size of ethanol, I usually call it a base, with the exceptions that I pointed out earlier. So here's water. It's smaller than ethanol. It's going to be a nuke, which means that this reaction is going to go SN1. So what's going to end up happening here? Well, in an SN1 mechanism, and I'll put a link here to a video in which I talk about that in detail if you've already forgotten it, my leaving group takes off first, giving me a carbocation. Now, the thing about carbocations is they can undergo rearrangements if doing so increases the stability. You'll notice that's a secondary carbocation. I've got a hydrogen right here that isn't drawn earlier because it's implied. That hydrogen can take these 2 electrons, walk over next door, and plop them right into that hole. That's called a hydride shift. If it does that, that ends up giving me my carbocation at this position. Now hopefully you can see I've gone from a secondary carbocation to a tertiary carbocation. A tertiary is more stable, so I will get that hydride shift. At this point, my nucleophile, in this case my water, is going to come in here. It's got its lone pairs. It will thrust them right into that hole. That gives me this. And now I have a second molecule of water that will come in here, deprotonate that, and give me my final product, which is that. I understand I've kind of made a mess and drawn things all over the board, so I'll go ahead and erase them and put them a little bit clearer. Hopefully you can see that. Let's move on to these examples down here. My leaving group is the bromine. Carbon it's stuck to, is it primary, secondary, or tertiary? It is secondary because it's bonded to two carbons, one down here and one to the left. Secondary could potentially be any of the above, so I'll go ahead and write all of them. SN1, E1, SN2, E2. I go to my next question. Is my nucleophile / base strong or weak? There's no sodiums, no lithiums, no potassiums. There are no localized and negative charges in that molecule. All I've got is lone pairs on the oxygen, which means that it is weak. Weak, what does that mean? It means a 1 reaction, so that could either be SN1 or E1. Next question, is my nucleophile / base a nuke or base? That all comes down to size with, once again, the exceptions I've talked about earlier. If it's larger than ethanol on paper, it's a base. If it's smaller than ethanol on paper, then it's a nuke. It's small enough it can get into a hole and kick off a leaving group, or get into a hole that's generated by a carbocation. The substitution reaction, that thing is bigger. It's tert-butanol. It's a big old bulky base. Bases prefer E reactions, so this is going to be an E1. What does that mean? Well, what it means, of course, is that this leaving group is going to take off, giving me a beautiful secondary carbocation. You can see, as with the previous example, that I can have a 1,2 hydride shift. The hydrogen walks next door with its 2 electrons. That gives me a tertiary carbocation. And at this stage, I can do an elimination. Of course, the base that's going to be used is this tert-butanol. It's going to be using its lone pairs to do the elimination. It could potentially eliminate across this bond to form a double bond, or across this bond to do a double bond. And it will do both in theory. The one that it's going to be the major product, however, is going to be the one that leads to the more substituted alkene according to Zaitsev's rule, which I'll post a link for right here. So of course that's going to be the one over here. So this guy's going to grab that hydrogen, dump these electrons down in there, and give me my final product, which is that. Now we'll look at this bottommost example. My carbon bound to my leaving group is this one right here, stuck to that iodine. Is it primary, secondary, or tertiary? Well, it's got a carbon down here and it's got a carbon to the left. That's 2 carbons. It's secondary. What does that mean? Well, it does mean that it could be potentially any of the above, so I'm going to write them all down. E1, SN1, E2, and SN2. Then I go to my next question. Is my nucleophile / base strong or weak? I've got a lithium. That is a group 1 atom from the periodic table, which I can think of as basically just being like a negative charge. It's going to pump its electrons onto that oxygen. That oxygen has a negative charge. Can that negative charge resonance delocalize? No, it can't, which means it's a localized negative charge. So that lithium tert-butoxide is a strong nucleophile / base. What does strong mean? Strong means it's going to be a 2 reaction, either an SN2 or an E2. So I'll cross off the 1s. Now I go to my last question. Is my nucleophile / base a nuke or base? Remember, that's all based on size. If it's ethanol or larger, it's a base. It's too big to get in there and do a substitution reaction. If it's ethanol, well, if it's smaller than ethanol, then it's a nuke. It's small enough that it can go in there and do a substitution. This guy is bigger than ethanol, at least when I draw on paper. So bigness implies that it's a base. So it's going to be, I can cross off SN2, it's going to be E2. So what does that mean? Well, what it means is that this guy is going to eliminate a hydrogen either to the left of the iodine or the right. And it will do a little bit of both, I'm sure, but the major product is going to be the one that gives us the most substitution. That is going to be forming the double bond right here rather than forming the double bond down here. That is according to Zaitsev's rule, to which I'll once again post a link right here. So that means, because this is an E2 reaction, this base is going to come in there and in one fell swoop grab that hydrogen, dump these electrons down, they close like a door on a trapdoor on a hinge, bam, form a double bond, kick off the iodine, and I end up getting this as my major product.